So the first lesson deals with vertical asymptotes. This is on page 25 and 26 of your unit handout. It's a fairly short lesson. The next one on horizontal will be more involved. We're going to be looking at equations of vertical asymptotes, and you already know, we're going to review, but you already know how to determine equations of vertical asymptotes. This is nothing new. What is new is describing a function close to the asymptotes, formally describing it. We've talked about this in Math 30-1, but we haven't formally described what's going on. And we're going to be using limits to describe the behavior of the function near a vertical asymptote. So to begin with, a vertical asymptote occurs at a particular value of x if there's a discontinuity of the function. So there's a break in the function, but it's more involved than that. If I just said there's a break in the function, unless the function approaches infinity or negative infinity, it's not an asymptote. If we have just a hole is a break in the function, but the graph is not approaching infinity or negative infinity when it gets close to that non-permissible value of a. I'll remind you here in terms of rational functions, and this is reviewed directly from rational functions and equations in Math 30-1, that if you have a function that's rational, which means it's a polynomial over a polynomial, and you have a factor of x minus a in the denominator, but you do not have a factor of x minus a in the numerator, then you will have a vertical asymptote at x equals a. We're really not concerned about holes or points of discontinuity, but if there were an x minus a in the numerator that canceled with the x minus a in the denominator, then the bottom line is there would not be a vertical asymptote. Okay, what does this mean? Well, if I just have a graph and there's a vertical asymptote at x equals a, which means the function has a quotient with a factor of x minus a in the denominator, the only way that graph is asymptotic is if when you graph the function, it has the following behavior close to the asymptote. It must look like that. It doesn't matter what it looks like anywhere else. And what's very important for you to understand here is we can describe this behavior in terms of limits. The limit as x approaches a from the right, which is the blue portion on the right of the asymptote, of the function, is positive infinity. The function is getting bigger and bigger and bigger as we get closer and closer to x equals a from the right. And when you take a look at the left of this example, the limit as x approaches a from the left of the function, well, when you look at tracking this blue graph closer and closer and closer to a for an x value from the left, the graph takes off down to negative infinity. So this limit is negative infinity. And what we have said prior to today's lesson is that those limits don't exist, but now we're going to talk about them existing as something that means something to us, positive or negative infinity. Incidentally, there's nothing to say that the graph has to look like that for it to be asymptotic. The graph could look like this, in which case both the left and the right hand limits of the function as x approaches a would both be positive infinity. Or it could be asymptotic with both of them in a downward direction. Or it could be, instead of this, it could be that the limit on the right is approaching negative infinity, or is negative infinity, and the left-hand limit is positive infinity. And lastly, I guess, just to point it out to you, it could be that maybe it's only asymptotic on one side. Maybe the function doesn't even exist over here, and that's a distinct possibility. So that's the definition of a vertical asymptote. As x approaches the location of the asymptote from the left or the right, the function approaches infinity or negative infinity. So, as an example, we're going to go back to the very first rational function that you learned about in Math 30-1, which is f of x equals 1 over x. I don't want to get into a table of values or any real details on how we come up with this sketch. It's a graph that we should know the appearance of. This graph has a horizontal axis on the x-axis. Now, when we first learned about this graph in Math 30-1, everybody, I just told you, well, it has a horizontal axis, and I didn't really discuss too much why. I can explain briefly why it does, but I don't want to get into too much detail about this horizontal asymptote because that's what the next lesson today is about. If you were to take a look at very, very large values of x in this function, the y-coordinate is found by taking 1 divided by that number. And if you take 1 divided by an exceedingly large number, you get an exceptionally small number. Which means that if I were to look at x equals 10 gajillion, the y-coordinate would be really, really tiny. So generally speaking, as you move further and further to the right, the y-coordinate drops off. I'll come back to that idea. Y equals 1 over x also has a vertical asymptote. And what the function looks like is this. It happens to be called a hyperbola. Those two pieces are symmetrical with respect to the origin. So by the way, this is an odd function. And we are asked to explain, look at what it says, explain the vertical asymptote in terms of limits as x approaches a. So what is our explanation here? Our explanation is the limit as x approaches 0 from the left. The vertical asymptote, everybody, has an equation of x equals 0. It's the y-axis. Of the function, the limit as x approaches 0 from the left of the function is equal to negative infinity, because on the left of that asymptote, the function is heading downwards without bound, without any breaking. It just keeps going. Similarly, the limit as x approaches 0 from the right of the function happens to be positive infinity. So that is the behavior. We've answered the question. That is the behavior of the function close to the asymptote on the left and the right for f of x equals 1 over x. Does anybody have any questions about those limits or this first little part of the lesson? So all of this is talking about the vertical asymptote. Asymptote is one of the weirdest words ever. There we go. As a side note, because we're going to talk about it later today, I could talk about the horizontal asymptote. The horizontal asymptote is y equals 0. That's the horizontal asymptote. And what I could say for that, and this should make sense to you, it's backwards from the vertical. I could say the limit as x approaches infinity of the function is 0. As x gets larger and larger and larger and larger, this graph, and I'm going to extend it a little bit, this graph will get closer and closer and closer to that y equals 0 value. It will never reach it, but as we approach infinity, the function will approach 0, which means the limit as x approaches infinity is 0. We could also say, and again, this is more about the next lesson, that the limit as x approaches negative infinity of the function is also 0, because if I extend this graph to the left, this graph is going to continue to get closer and closer to that line where y equals 0, and as a result of that, the function will approach 0, so the limit as x approaches negative infinity is 0. Any questions about that added bit of information in blue? All right, so a function is given by f of x equals x cubed over x to the 4 minus x. Determine the equations. Look at what we have to do. Find the equations of all vertical asymptotes and use limits to describe what the graph is looking like on both sides. Well, the first thing you want to do is express this function in factored form. And I can factor out an x and have x cubed minus 1. I can factor that further into f of x equals x cubed over x times x minus 1 times x squared plus x plus 1. This is a difference of cubes. X cubed minus 1 cubed. Then it factors into x minus 1 and then x squared plus x plus 1. Remind you that it actually factors into x minus 1 and x squared plus 1 times x plus 1 squared. I don't know if you remember, but one of the things I told you is when this goes way back to probably the first lesson in this course, when you factor a difference of cubes, this piece of the difference of cubes is never factorable. And if you were to calculate the value of the discriminant here, you would get a negative discriminant. So not only is it not factorable, it does not have any zeros. So what are the equations of the vertical asymptotes? Well, we have a non-permissible value at 0 because of this factor, which means we have a vertical asymptote at x equals 0. We also have a vertical asymptote at x equals 1. So now we have to determine the behavior of the function close to those two asymptotes. Any questions about getting those two equations of the vertical asymptotes? Okay, so this is what we need to do. We need to find the limit as x approaches 0 from the left of the function. And I'm going to write out the function in factored form. So, clean that up a little bit. And I have a correction to make. It's a pretty serious thing that I forgot to look at before. Can somebody tell me why there is no vertical asymptote at x equals 0? It didn't even dawn on me to look at this. There is no vertical asymptote at x equals 0.
And cancel the x on the bottom.
Perfect, Cambry. We have x cubed on the top and we have x on the bottom. So this thing simplifies to f of x equals x squared over x minus 1, x squared plus x plus 1. And that dawned on me because I was just getting ready to say to determine the value of this limit, we have to simplify it. But we should have simplified it first so that we can identify the asymptotes. This is from Math 30-1. If you have a factor that cancels, if you have a factor that cancels, then it's no longer an asymptote. So we're not worried about 0. We're worried about 1 from the left. And also, we want to find the limit as x approaches 1 from the right of this thing. So this goes back now to the lesson that we had on left and right-handed limits. How are we going to do this? Well, what we are going to do is look at the fact that when I put in a number very, very, very close to 1 in the top, when I square it, I'm going to get a number very, very close to 1. I'm actually substituting in a number in my brain that's close to 1 from the left, like 0.99999. Now, what happens when I put a number very close to 1 into this factor is I get 3. I get something that's very close to 3 because a number very close to 1 squared plus a number very close to 1 plus 1 will give you 3. I'm going to leave this part alone just for a minute. When I do the same thing for the other one, when I put a number in very close to 1, like 1.0001, because it's now from the right, the numerator will still approach 1. The denominator will still have this factor which will approach 3. The difference is that x minus 1. When I put a number in for x in here that is close to 1 from the left, this will be very, very small. I don't want to write 0 here. It will be a wee number, a tiny, tiny number. For example, a number close to 1 from the left would be 0.999999999, and if you subtract 1 from that, you're going to get a very tiny number, but it's going to be negative. And that's the key idea here. Over here, if you put in a number in here like 1.0000000001, you are also going to get a very tiny number, but it will be positive. Now we need to talk briefly about what I mean by a very tiny number. That wee number, that tiny number, is infinitely small. And when you have a non-zero number like 1 over an infinitely small number like 3 times this negative number, you're going to get infinity. And it's going to be negative because we're dividing by a negative. You know, if you wanted to, you could try this with your calculator. If we take 1 divided by, just type 1 divided by 0.0000 and sit there all day and continue to type a whole bunch of zeros and then end it with a 1 or a 5, you're going to get an explosively large result. So essentially, when you have division by a number approaching 0, these are both, this one and this one, they are both approaching 0. You are going to get an infinitely large result when you divide by a number approaching 0. The difference is that on the top denominator, this one, the bottom is approaching 0, but it's doing it with a negative value to it. So that's why we get negative infinity. All we have discovered here, everybody, is that when you look to the left of the asymptote, the graph will go down, and when you look to the right, it will go up. Any questions with A? Did you have to think of it this way? Did you have to think of it this way? No. You know what you could have done? You could have just taken the original function. You can even use this one and put in a number like 0.9999 and see what you get. And I guarantee you, you will get a negative number, and it will be very, very large. Okay, let's take a look at B. Find all x and y intercepts. So to find an x-intercept, we're going to let y equal 0. And I don't know that we really do this too much in Math 30-1, so I'm going to explain it in more detail. This is not a complicated equation to solve. You don't have to cross multiply. You don't have to do anything except look at the numerator. And here's the logic. If that entire fraction, which is y, is equal to 0, then the only way that can be true is if the top of the fraction is 0. This is the only way in the universe you can have a fraction equaling 0. So what you end up doing is you end up saying x equals 0 because of the numerator. X equals 0 is a value in the numerator that will make it 0. However, and this is a tricky one, but x equals 0 is non-permissible. Because there's a factor of x in the denominator. This function has a factor of x in the denominator, which means x cannot equal 0. I know that that cancels, and as a result, we don't have a vertical asymptote there, but we still have a non-permissible value. How many of you do remember what's going to appear on the graph at that point? So we said we had non-permissible values. We said x cannot equal 0 and x cannot equal 1. At 1, we had a vertical asymptote. Does anybody remember from 30-1 what you have here? It is a hole, Aaron. That's exactly right. Or if you want to sound more sophisticated, I like just saying hole, you could say a point of discontinuity. There's a hole there. So the bottom line here is there's no x-intercept. Or sorry, there's no y-intercept. No, x-intercept. That's what we were working on. Let's find the y-intercept now. To find the y-intercept, this is not going to take a lot of room to do this. The y-intercept is found by letting x equal 0. But when you put 0 in for x, you're going to get y equals 0 over 0, which isn't defined. So this graph has no x and y intercepts. None. It's a tricky graph. Any questions with B? All right, so now what we're going to do is put it all together. We're going to do a first derivative test. In other words, we're going to find the first derivative, complete a first derivative chart so that we can look at what the graph of this function looks like without using a graphing calculator. Now, the function itself was y equals x cubed over x to the 4 minus x, but there is nothing wrong with simplifying any algebraic expression before you differentiate. We've talked about this before in the first unit. So if I factor an x out of the denominator and cancel it with one of the x's in the numerator, this gives me a function whose derivative will be the same as the derivative of the function before x was canceled. As well, note that I'm not going to differentiate it by using the factored form of the denominator. I'm going to differentiate it from this form because it will be easier. So what will dy dx be equal to? It's a quotient rule. I have to take the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. And I'm going to double check everything, as should you. The derivative of the top is 2x, that's fine. The bottom is x cubed minus 1 minus the top, which is x squared, and the derivative of the bottom is 3x squared. So we're going to factor the numerator. I can take out an x, but that's it. And I will have left 2 times x cubed minus 1 minus 3x cubed. We'll double check that. Out of the first term, I can't really point at anything, so I'll use highlighters. Out of this term, I took an x out, so I'm left with the 2 times x cubed minus 1. Out of this term, which is 3x to the 4, I took an x out, so I'm left with 3x cubed, and I was subtracting. All right, clean it up a little bit more. dy dx equals x, and then what do we have here? I don't want to skip any steps. 2x cubed minus 2 minus 3x cubed. So the 2 times the x cubed is 2x cubed. The 2 times the negative 1 is negative 2. And then I have my minus 3x cubed, which means dy dx is equal to x times, I wanted to take out a negative right here, but I'm not going to. We'll worry about that in a second. So 2x cubed minus 3x cubed, I'll just highlight what I'm thinking here. 2x cubed minus 3x cubed gives you negative x cubed. And I'm going to take out a negative finally, and I will have a relatively simplified form of my derivative. dy dx is equal to negative x times 2 plus x cubed over x cubed minus 1 squared. So that's the derivative of the function. I just want to go back and double check my last couple of steps to make sure. Might as well just go from the beginning. Derivative of the top times the bottom. I'm looking here when I talk about top and bottom. Minus the top times the derivative of the bottom over the bottom squared. I took out an x. I multiplied that 2 through to get 2x cubed minus 2 minus 3x cubed. 2x cubed minus 3x cubed is negative 1 x cubed. I then took out a negative 1. I think we're fine. So we're doing this so that we can find the first derivative's behavior over the different intervals. The critical values of x, we have a 0 because of that factor of negative x. We have a 1 because of x cubed minus 1. Or if you factored x cubed minus 1, you would get a factor of x minus 1. I'm going to tell you in a bit why we don't need to factor it. And then we also have the cube root of negative 2. Because when I take a look at that factor of 2 plus x cubed, it can be equal to 0 if x cubed is negative 2, which means x is the cube root of negative 2. So we have 3 critical values of x. Any questions with getting those three critical values? Okay, so that means we're going to split up all of the real numbers from negative infinity to positive infinity. Now there's a bit of a hitch in this because we do have non-permissible values, but the two non-permissible values of the function turn out to be critical values of the derivative, and that must always be true. Because if you're not allowed to use x equals 0 in the function, then there's no way the derivative can be defined at x equals 0. So we don't need to overanalyze the domain in this example. We're going to cut this at negative cube root of negative 2. Cube root of negative 2, by the way, is the same as the negative of the cube root of 2. We need to cut it at 0, and we need to cut it at 1. We will have an interval in our first derivative table or chart from negative infinity to the cube root of negative 2. Then from the cube root of negative 2 to 0, from 0 to 1, and finally from 1 to infinity. A double check as you go from critical value to critical value, the numbers should increase. And they are increasing. Remember that I made that mistake of having them in the wrong order in one of the problems that we did. We want to double check that. The other internal kind of double check here you can do is if you have n critical values, then you're going to have n plus 1 intervals. So since we had 3 critical values, we get 4 different intervals. Across the top, we're going to put the factors of the derivative. One of the factors is negative x. One of the factors is 2 plus x cubed. And one of the factors is x cubed minus 1 squared. You might remember me saying I'm not going to worry about factoring x cubed minus 1. And the reason is the whole thing's squared. So whatever x cubed minus 1 is, positive or negative, when you square it, you're going to get positive. Negative x has a 0 of 0, so the turning point for that factor is when it crosses this line. It's when it crosses that value of x of 0. But since the leading coefficient of this is 0, it doesn't go from negative to positive, it goes the other way. It goes from positive to negative. Now, you can treat this middle factor as a linear one. In other words, you can use the same rules we have. But if you are unsure, then take a number that's in this interval. And I don't know exactly what the cube root of negative 2 is, so you know what? Why don't we find out approximately what it is? So that would be negative 2 raised to the 1/3. Could you use the cube root function on your calculator? Sure. But it's about negative 1.25. So if I put in a number like negative 10, in here, I can work out whether 2 plus x cubed is positive or negative, and I'm going to discover that it will be negative. Thanks for catching that, Aaron. So are there any max mins here? Everybody think of that. Look at your last column and determine if there are any max mins.
Yes. Or
What would be here, Aaron?
that would be
Yep.
and then a maximum.
Well, let's take a peek at the graph. I'm not going to graph it. Let's just use our graphing calculator. I'm going to need your help here. I believe it was x raised to the 4. No, it was x cubed over, in brackets, x raised to the 4 minus x. Can I get somebody to verify that?
Yes.
Okay. I'm going to set this up on my graphing calculator using the critical values as kind of a point of reference. There's something important that happens at the negative cube root of 2 or the cube root of negative 2, which is about negative 1.25. There's also something important that happens at 1. So in my window settings, I'm going to go from negative 3 to 3. We could go to my table now and just see what the behavior of this graph is in that region. I'm going to set it to start at negative 3 and go up by 0.5. I'm just looking in my table to find out what kind of y coordinates. The y coordinates are incredibly small, very, very small, and then they start getting bigger and smaller again, but it's looking like negative 1.5 to 1.5 would do it. So there is an asymptote at x equals 1. There is a minimum at the low part of that valley on the left of the graph, which is at, I'm assuming that's the cube root of negative 2. And there's a maximum at 0, which is really weird because there's no point at 0. Right? I'm going to remove the axes from the view. And I'm going to go zoom decimal. Don't worry about why I'm doing this. You can see that at this point, right here, there's a minimum. That would be at x equals the cube root of negative 2. At this point, there's a maximum, which again is very weird because if you look carefully at that point, there's a hole there. If you go zoom decimal, you very often see the hole. And that maximum is occurring in the vicinity of 0. Thank you for catching that, Aaron. So I don't know how much time we're going to work on these. Well, let's say about 20 minutes. So about 10 to 2, I'm going to move on and look at horizontal asymptotes, which again is something you studied in 30-1, but we're going to look at it in a little more detail today.